In this section, we're going to take a look at what are called Taylor and Maclaurin series. And what this will allow us to do is take a lot of the functions that we've worked with and write them as infinite series. So we're going to start with this generic form of a power series here. And what I want to do is first let's just write it in its summation form, right? So you can look at it in that way also. So we're talking about this power series where I've got coefficients that depend upon n times this x minus a to the nth power. All right, so what I want to do is I want to take derivatives of this thing and try to get a sense for a pattern as we go. All right, so first of all, you know, when we take the derivative of c0, right, we of course get 0. When we take the derivative of a constant times x minus a, that's going to just give us that constant back. Here, when we take the derivative of a constant times x minus a squared, bring the 2 down in front, times x minus a to the first. And here we're bringing 3 down front, times x minus a to the second. And 4 down front, times x minus a to the third, and so on. All right, and then what we want to do is we want to actually evaluate the derivative at a, but of course that means that you're going to plug a into all these spots where you see an x, which of course is going to zero out all these terms except for the c1. So when you evaluate f prime at a, the answer is just going to be that first constant. All right, so now let's try the second derivative. Okay, so if I take f prime, if I take the derivative of c1, that's going to be 0 plus 2c2 plus, and now as I show this pattern here, I'm actually going to purposefully not multiply stuff out. So instead of saying 6 times c3, I'm going to say 3 times 2 times c3 times x minus a, and then plus 4 times 3 times c4 times x minus a squared, and so on. And then again, let's evaluate this at a. All right, so we're putting a in here, we're putting a in here. And so the only thing that survives is 2c2. Oops. So to kind of continue this pattern here, sorry, I'm having a little trouble with my mouse. Let's now do the third derivative. So for our third derivative, we're going to end up with the 2c2 zeroing out. Then we're going to get 3 times 2 times c3 plus 4 times 3 times 2 c4 and so on. And then when I evaluate that at a, I just get 3 times 2 times c3. All right. And so now the idea is, can we kind of establish a pattern here? Well, as I go back up to the top, f prime of a was c1, f double prime of a was 2c2, f triple prime of a was 3 times 2 times c3. Okay, so I think we see a pattern emerging here, but I do want to make one quick adjustment, and that is, oops, let's go back up to this one, and let's go ahead and let's stick a 1 in front of it. So another way of saying this would be or 1 times c1. And certainly I think you'd be okay if here I re-express this as 2 times 1 times C2. And then down here, I could re-express this one as 3 times 2 times 1 C3. So the pattern that emerges here is that it seems like whatever derivative we happen to be at, and by the way, this notation here, you've probably seen this before, but this just means the nth derivative, right? At some point, we don't want to just keep putting the little slashes for the primes, right? So if I had to guess, I'm going 3 times 2 times 1 for the third derivative. I'm doing 2 times 1 for the first derivative. So I think what I'm probably doing is I'm starting at n and I'm counting all the way down and multiplying. So that would be n factorial, right? Because this is 3 factorial. And then we always have the coefficient that goes along with how many derivatives you took. So Cn. And so what this tells us actually is a formula for what Cn is. So this is f, the nth derivative of f evaluated at a, over n factorial is the Cn for the series n equals 0 to infinity Cn x minus a to the nth power. All right, so what does this tell us? So here's a theorem. It says, if a function f has a power series representation, sometimes we call it an expansion at a. So if you can express a function as this infinite series, then you know that the coefficients are given by this formula here that we just came up with. And we call this representation of a function the Taylor series of the function at a. All right, so here's our formal introduction here. So we're saying if, and this is a big if f has a power series expansion at a, then it must be of the following form. And then that's the summation notation we just had, and then this is it written out. And then there's a special case of the Taylor series called the Maclaurin series, and the Maclaurin series is just one where you're centering at a equals 0. So if instead of centering it at a, you just center it at 0, then of course x minus a to the n just becomes x to the n, and then you're plugging 0 in for the where you're evaluating those derivatives. All right, so in example 1, it asks us to find the Maclaurin series for the function f of x equals e to the negative x, and then it wants us to find its radius of convergence. All right, so we've got the formula right there in front of us. So what we can do is basically take derivatives, and you can maybe see why I picked e to the negative x, because it's got a pretty easy derivative, and then evaluate those at 0, right? So first of all, f of x equals e to the negative x, so f of 0 is equal to 1. But then if I take f prime of x, that's going to equal negative e to the negative x, so f prime of 0 is equal to negative 1. And it doesn't take us too long to see the pattern here, right? Chain rule brings the negative down, so now I'm back to a positive. F triple prime of x is back to negative again, so f triple prime at 0 is back to negative 1. So all we're doing is we're alternating between 1 and negative 1 for these values up here. And so we know how to do that, right? To alternate between 1 and negative 1. what we can do is say n equals 0 to infinity, and just go -1 to the n, so that whenever n is even, you get +1. Whenever n is odd, you get -1. All right, and then we know we have to put n factorial down below. And then we just go ahead and say that's times x to the n. So this is the Maclaurin series for f of x is equal to e to the -x. Okay, and they also asked us to find the interval of convergence. And so if we're going to find the interval of convergence for this series here, let's think about how we might do that. So we know that we can do that using ratio test, right? So this would be -1 to the n plus 1, x to the n plus 1 divided by n plus 1 factorial, and then -1 to the n, x to the n over n factorial. All right, but we can ignore the -1s, right, because we have absolute values. X's could be negative, so we're going to keep absolute values on those. So what we end up with is, this is the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. So then we know we've played this game before with the ratio test. All right, rewrite that in that way, rewrite this in this way. And then we can see some nice cancellation. Sorry, that went off the screen, but that's an x to the n down there. I guess I can fix that so that it's a little more visible. All right, so then we can cancel a bunch of stuff out there. So we have that, and that, and that, and that canceling. And so, of course, the limit here is equal to 0, right? Equal to 0 for all x, right? It doesn't matter what you stick up here. This n plus 1 in the bottom goes to infinity, so makes the whole thing go to 0. So what that means is that the interval of convergence, or the radius of convergence, is infinity. Radius of convergence is infinity because the interval of convergence is all real numbers. All right, now the one thing to say about this is that we can see that this infinite series is convergent everywhere, which is great, but that doesn't necessarily mean that it looks exactly like our function everywhere. Now, in this particular case, it does happen to, and we'll address that question more carefully a little later. So since this one's an example where its Maclaurin series does look just like it for all x's, let's kind of get an idea of what that actually means. So let's pull up a calculator here. All right, so what I've done is I've put in our function e to the negative x as the blue function, and then the first 5 terms of the series, right? So obviously this is not going to be a perfect match because I'm not using all of the terms, but this should kind of give me an idea. So let's go to, actually let me deselect y2 real quick and go to graph. So here's e to the negative x, right, a decaying exponential function. So now if I go and I put in this red graph, you can see, at least for a while, how well it mimics it, right? And that's just using 5 terms, right? So the more terms I use, the more, the more accurate it'll be out here. So this is what we're talking about. We're taking a function like e to the negative x, and we're representing it as an infinite series, which if you kind of stop and think about it, it is kind of cool. All right, so moving on to the next example here. So let's take another function that we're definitely familiar with. So it's going to ask us to find the Taylor series of this function at a equals 2. So the last one we did was a Maclaurin series. Here we're going to actually do a Taylor series, right? So a Taylor series is one that's centered at a different place. And if you go back to the graph of our e to the negative x, remember the place where it was most accurate, even just using a few terms, was like right at 0. That's because we centered that Maclaurin series at 0. So the idea of centering it somewhere else, like at 2, is that, okay, it's going to be kind of most accurate there, even when you're not using all the terms. All right, so remember, here's our general form of our Taylor series. Our Taylor series is n equals 0 to infinity, the nth derivative evaluated at a over n factorial times x minus a to the nth power. All right, so we need to set about figuring out these nth derivatives. And what I suggest is when you do this, don't be in a hurry to simplify anything. Just kind of keep it, continue to write it with, just numbers multiplied together, like we did back here on page 1, right, where we did 3 times 2 times C3, right? Kind of follow that same pattern as you do this. So n equals 0 means you're not taking any derivatives, right? So we'll say f of x, of course, is just 1 over x. And so f of 2 is 1/2. All right, so now let's take the first derivative, right? So of course we know that f of x is also x to the negative 1. So the first derivative is going to be negative x to the negative 2, right? Which is negative 1 over x squared. So then f prime of 2 is going to equal negative 1 over, and I'm not going to be in a hurry to simplify, I'm just going to say 2 squared. All right, so now let's do f double prime of x. So that's going to be, all right, well really up here we had a negative 1 times negative 2, right? So now it's going to be a negative times a negative, but it'll be 2 times 1 times x to the negative 3, which is 2 times 1 over x cubed. So then f double prime of 2 is 2 times 1 over 2 cubed. So f triple prime is going to be negative 3 times 2 times 1 times x to the negative 4, which equals negative 3 times 2 times 1 over x to the 4th. So f triple prime of 2 is -3 times 2 times 1 over 2 to the 4th power. All right, so I think we can probably see pretty well now what our pattern is. So, and going back up here to save space, I think it's safe to say that Fn of 2 is, well, we definitely have this factorial action happening, right? And the place that I'm starting my multiplication is the same as my derivative, so I think I'm definitely going to have an n factorial up here. But I also see that it alternates between positive and negative, and it's negative whenever we're taking an odd derivative, so that's going to mean -1 to the n divided by, and then it looks like we have 2 raised to 1 more than the power of the derivative that you're at. So when I don't take a derivative, I'm 2 to the 1. When I take the first derivative, I'm 2 to the second. The second derivative, I'm 2 to the third. So I think what I'm doing here is I'm saying over 2 to the n plus 1. And so when it comes to the series here, Fn of 2 divided by n factorial, we'll just take -1 to the n times n factorial over 2 to the n plus 1 times 1 over n factorial, right? So this n factorial I'm dividing by here is this same 1. And then that's kind of nice because our n factorials just cancel out. So we get a pretty simple coefficient here. So it'd be -1 to the n over 2 to the n plus 1. And that's our coefficient. All right. Now, of course, we do want to talk about what our radius of convergence is. Right, so is this going to be convergent for all of our x values, just some? What's the story there? So let's now set about the radius of convergence. So maybe just let's put this in a different color. So here's what we have so far. That our Taylor series, put it down at the bottom here, I guess, a little bit further. So our Taylor series is equal to the sum from n equals 0 to infinity of -1 to the n over 2 to the n plus 1 times x minus 2 to the nth power. But what we need to attach to this is what the radius of convergence is, okay? Or interval of convergence. So we'll say for x between what numbers, right? Maybe it's -infinity to infinity, we'll see. All right, so we know that to figure out this interval of convergence here, that's where we're going to work on the ratio test. So we'll take the limit as n goes to infinity of -1 to the n plus 1 x minus 2 raised to the n plus 1 all divided by 2 to the n plus 1, right? We already had n plus 1 down there, right? So then it's plus another 1, all divided by -1 to the n, x minus 2 to the n, divided by 2 to the n plus 1. and we've done this many times, so this will be the limit as n goes to infinity of x minus 2 to the n plus 1 over 2 to the n plus 1 times 2 to the n plus 1 over x minus 2 to the n. All right, and then we'll see what kind of cancellation can happen here. So this is equal to the limit as n goes to infinity. So up here we can break this up, x minus 2 to the n times x minus 2 divided by 2 to the n plus 1 times 2 to the n plus 1 on top over x minus 2 to the n on bottom. And so these all cancel out. And so this is all equal to x minus 2 in absolute values, of course, over 2. Okay, and kind of struggling to keep everything on the same page here, but I think we can manage over here on this right part. So this is saying then that we've got our, we know, right, that we need this limit. We need this limit to be less than 1, right, to guarantee convergence. And then x minus 2 is less than 2 in absolute values. And so that, of course, means that x minus 2 is between negative 2 and 2. Which means that x is between 0 and 4. Okay. And of course, please do remember that you are required to check the endpoints. We have done this a number of times in earlier sections, checking the endpoints, but that means you actually plug in 4 and you actually plug in 0. So I'm not going to actually do this. I'm just gonna make a little note here. And that is the series diverges at 0 and 4. Okay, so checking the endpoints, I find a divergent series. Okay, so what this tells me is that overall we have our Taylor series, and it is convergent for x is between 0 and 4. Or another way of saying it is that the radius of convergence is 2. All right, but let's work with this thing a little bit more. So let's actually take this Taylor series and calculate the Taylor series up to the fourth of up to n equals 4 to approximate the function g of 3. So the idea is this function is supposed to look like this Taylor series, at least for certain x values. So if I want to approximate what g of 3 actually is, okay, then what I can do is say, well, that should approximately be my Taylor series at 3. And remember from the last page, right, 3 is within this interval of convergence, right? So the series does converge at 3. So I'm going to evaluate this at 3, right? And so let's write down up here again what our Taylor series was, right? It was n equals 0 up to infinity of -1 to the n over 2 to the n plus 1 times x minus 2 to the nth power. All right, so the t sub n is the nth degree Taylor polynomial of f at a, right? So you're just going to stop at the 4th degree. So that would be, the first 5 terms, I guess. So this is equal to, so when I plug n in for 0, I'm going to get 1/2 times 3 minus 2 to the 0. Then I'm going to get minus 1/4 times 3 minus 2 to the 1 plus an 1/8 times 3 minus 2 squared. And of course 3 minus 2 is 1, so that's kind of boring, but I'm going to continue to write it just so it's really clear where each of these terms is coming from. All right, and when I do that summation, I get about 0.344. All right. So we might wonder, okay, how accurate is this? Well, the nice thing about our function, g of x, is that it's an easy function, right? Remember, g of x is 1 over x. So what I can do is I can calculate the difference between our actual function value and our Taylor polynomial. And so because I know that g of 3 is just equal to 1/3, then I can say that the remainder, when you use the 4th degree polynomial of the Taylor series at 3, is the difference between g of 3 and the Taylor series at 3. And g of 3 is 1/3. The Taylor series was 0.344. And so that gives us an approximate remainder of negative 0.011. So that means that our function is kind of undershooting the, the Taylor series is a little bit bigger than the actual, right? So that's why we have this error here of negative 0.011. All right, now one of the things that we need to now worry about is the question that I kind of brought up earlier, is we might have a convergent series, but does that necessarily mean that it converges to the function itself? Okay, so this theorem talks about that. So it says that if f of x is equal to the nth degree Taylor polynomial plus some remainder, and you could always say that, right? That regardless of how close the Taylor polynomial is, that if it was way off, the remainder would just be bigger too. It says where t sub n is the nth degree Taylor polynomial of f at a, and the limit of the remainder goes to 0 as n goes on, then what we say is f is equal to the sum of its Taylor series. Okay, so just like we seem to see in our first function where we looked at it in the graph of e to the negative x, it seemed like the Maclaurin series there really did approximate well the original function. We're basically just saying here, yeah, as long as the remainder is going to 0 in the long run, then your function is equal to the sum of its Taylor series, at least over that interval of convergence. Okay, and so in order to determine if you in fact do have a function that is equal to the sum of its Taylor series, it becomes necessary to kind of get a handle on the remainder. And so Taylor's inequality says this, okay? If you can find a number m where the n plus 1 derivative of your function is less than or equal to that number, for all x within a certain amount of a, right? So in other words, as long not straying too far from a, or straying only this far from a, I should say, then the remainder of the Taylor series satisfies this inequality. Now, this inequality can be proven, and the space below, I was going to prove kind of an easy case of it. I don't think I'm going to do that because this is over video. It takes quite a while. So I think I'm going to skip over that proof part. The proof is not easy, but it is, you can definitely follow it, but it would just take a real long time. So when we're working with Taylor inequalities, what I want us to remember here is that we need to basically find the the whatever this n+1 derivative, and if we can find that, then basically whatever that value is, the biggest that value can ever get, that's going to be your m. Okay, when you're working with this inequality. All right, so moving on to the next page where we actually do an example with this. Okay. Example 3 wants us to prove that the function e to the negative x, the one we started with, is equal to its Maclaurin series for all x. Okay. So what Taylor's inequality said is that what we need to be able to do is get a handle on the n+1 derivative. Now in this particular case, that's fairly simple because we've already done the pattern that says f of x equals e to the negative x. F prime of x is equal to negative e to the negative x. F double prime of x is equal to e to the negative x, right? So we know that it's just alternating. So if you take the f sub n+1, fn+1 derivative, and you take its absolute value, that's just always going to equal e to the negative x. Okay, and so here's what the Taylor's inequality says is that the remainder is going to be less than or equal to this m over n+1 factorial times the absolute value of x minus a to the n+1, okay? And we just got a handle on how big the n+1 derivative actually is, right? It's never bigger than this. And so in Taylor's inequality, this needs to be true for anything where x minus a is less than or equal to some number d. So what we're going to do is we're going to just let d be any positive number. It could be anything, right? You could pick something huge. You could pick something like 1,000, okay? And let d be any positive number. And so, of course, what we're trying to do, let me click back real quick, right? In Taylor's inequality, right? What we have to show, right, is that the remainder is bounded by this. And then if we can show that the limit of this remainder then therefore must be 0 for everything where x minus, and in our case it's a 0 because it's Maclaurin series, so the absolute value of x is less than or equal to this d. If d doesn't have any limit on what it can be, which it doesn't in our case, then we'll have proved what we need to prove. So we're letting d be any positive number. Okay, so what we can then say is that for the absolute value of x being less than or equal to d, it must be true that the absolute value of the n+1 derivative evaluated at x, it must be true that that is less than or equal to e to the positive d. Okay, so why is this? this is because x has to be between d and negative d, right? Okay, and so what is going to give you the very biggest number here? The very biggest number here is going to be when you stick negative d, right, into this spot for x. Then e to the positive d is the very biggest that could ever be. So that is your m. So what this means is that when we want to calculate the limit of our remainder, we know that the limit of the absolute value of our remainder has got to be bigger than or equal to 0. No question about that because it's an absolute value. But that then also has to be less than or equal to the limit as n goes to infinity of this, right? Because of Taylor's inequality. And so, of course, our a is a 0, remember. So this is just going to be m, which we decided is e to the d, over n plus 1 factorial x minus 0 to the n plus 1. All right, and then on the previous page, I glossed over this, but let me go back to our previous page. At the very bottom, there's a little helpful hint that says anytime you're taking the limit as n goes to infinity of x to the n over n factorial always wins, and the limit is 0. So we can feel free to use that here. So we have an x to the n plus 1 here. We have an n plus 1 factorial on the bottom. This is a constant, remember, right? Because we already set what our d was. And so this has got to be equal to 0. So what we've just proved is that the limit as n goes to infinity of our remainder is equal to 0 for all x in negative d to d, okay? But of course, you know, because that's what we started with the assumption. But we didn't say what d was, right? So d could be 1,000, d could be 1,000,000, d could be 1,000,000,000. So because we left d arbitrary, we know that the function e to the negative x is going to be equal to its Maclaurin series anywhere. So we've done a few examples in this section where we are looking at a function that we want to write as a Taylor series or a Maclaurin series, and we take a bunch of derivatives and use the formula for the coefficients to figure out what that series should look like. But we also may want to just, you know, rely on some work that's already been done. So here are some functions that we, you know, have some experience with, and their Maclaurin series. And so sometimes you'll be asked to do problems where you're supposed to reference this table and then answer questions based on that. So just, you know, before we move to the next example, just notice how kind of really cool this is. So what we're saying is e to the x, right, is equal to this infinite series. And because the radius of convergence is infinity, that means this infinite series is equivalent to this function everywhere, right, for every x. The same thing for sine of x and cosine of x. They have Maclaurin series too. And by the way, remember Maclaurin series you're evaluating at 0, right, instead of some other number. That's what makes it a Maclaurin series. So the reason why you're going every other with sine and cosine is because you know that the derivative of sine is cosine and the derivative of cosine is sine. So they just alternate back and forth in terms of their derivatives. And you know that the sine of 0 is always 0. So where you're seeing terms missing, the reason that they're missing is because that's where you're evaluating the sine function at 0. And where you see the terms, that's when you're evaluating the cosine at 0, which is 1. So just kind of an interesting thing to note there. And then one other little notational thing here, this last one, this right here is what's called a binomial coefficient. This is combinatorics. It's called k choose n. And so here's the formula for it. If I ask you a question like this, I would give that to you. I wouldn't expect you to know that. All right, but let's take a look at example 4. It asks us to use the Maclaurin series given above for the tan inverse of x to find the Maclaurin series for 1 over 1 plus x squared. At first, that might be a little bit puzzling until you remember from Calc 1 that the derivative of tan inverse is 1 over 1 plus x squared. So we'll start just by writing out exactly what the table tells us, right? We'll say tan inverse of x is equal to the sum from 0 to infinity, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1. All right, so we learned, oh, and by the way, let's make a note here. According to the table, the radius of convergence is 1. So this is only true for going between negative 1 and 1. All right, so we learned that we can take the derivative of infinite series term by term. So what we'll do next here is we'll say, let's take the derivative, d dx, of the tan inverse of x, and then also take the derivative of each of these term by term. All right, so on the left, we know what that is, right? That's 1 over 1 plus x squared. On the right here, we're just going term by term. So, we'll still have the summation. And then, still have negative 1 to the n. That's unaffected by taking the derivative. So then we multiply by our exponent. And then we take 1 away from the exponent that's there. And you can see that this one cleans up really nicely. And so we can do a little bit of canceling out. And so we end up with an answer that says the Maclaurin series then for 1 over 1 plus x squared is equal to negative 1 to the n, x to the 2n. And if you think about what this is, we also could have really easily written this as a power series where you stick negative x squared in for x in the power series, which then would still yield the same thing. And then let's also note this also has a radius of convergence of 1, right? Because what we learned in a previous section was that if you have a particular radius of convergence and then you take the derivative or you take the integral, you maintain the same radius of convergence after doing that. All right, so here's our last example of this section. It's kind of a cool example. It wants us to evaluate this integrand as an infinite series, and we want to approximate the integral to within 3 decimal places. This particular integral, by the way, is going to give me the area under that curve between negative 1 and 1. And the significance of that curve is that it is a normal curve. And so depending on if you've had statistics or not, this may be meaningful to you. So this is the normal curve or the bell curve that occurs in statistics and in all sorts of real life phenomena. And so if here's 0, the idea is they want to know the area between negative 1 and 1. And a statistical fact that we know is that if we have a normal curve, the percentage of the curve between negative 1 and 1, which is going to correspond to the area here, is about 68%, so 0.68. So we kind of know what we should get here. So let's see if we can use infinite series to get this, because this integral right here is not one that we're going to be successful doing with your familiar integration techniques. Okay, so to start off here, let's work on expressing this function e to the negative x squared over 2 as an infinite series. Okay, now here's the nice thing. I already know what e to the x looks like. So based on the table from the previous page of our notes, I can simply write this down. E to the x is n equals 0 to infinity of x to the n over n factorial. So we have that for e to the x. But let's understand that all that's going on here is we have something a little bit more complicated, but it's still the function e to something. So that means that I can take that something and put it in place of where x is. So just to make this a little bit cleaner, I don't think anyone would complain if I wrote this like 1 over n factorial times x to the n. So following that idea, let's go 1 over n factorial, and then it's going to be negative x squared over 2 to the n. And we can clean this up a little bit. This would be n equals 0 to infinity, and it would be negative 1 to the n, x to the 2n over n factorial 2 to the n. So when I do this integral here, I'm going to be integrating from negative 1 to 1. I'm going to pull out this 1 over root 2 pi because it's just a constant anyway. And I'm just going to be integrating term by term this infinite series. Now this thing, starts to get a little bit messy when you're thinking about the integral, but remember the only thing you have to really think about is the x, right? So when I take the integral, what I'll have is negative 1 to the n is unaffected, but I'm going to add 1 to the exponent. I still have my n factorial down here. I still have my 2 to the n down here. And then I just have to remember when I take an antiderivative, I'm also going to divide by that new exponent. And then I am evaluating that from negative 1 up to 1. Okay, so going ahead with doing the evaluation, leave this outside again. This will be the sum from n equals 0 to infinity. And what I'm going to do is I'm just going to do this subtraction term by term. So I will just put the 1 plugged in. First. Minus, oops, my eraser there. Minus negative 1 to the n times negative 1 to the 2n plus 1 divided by n factorial 2 to the n 2n plus 1. And sorry, I've kind of gone off the screen here. Okay, so as I move down, I want to obviously look for opportunities to simplify this. I'd much rather that this just be a single term if I can. And there is some stuff I can do here, because in that second term, -1 to the 2n plus 1 is going to be the same as, so I'm going to write this one first, -1 to the n, -1 to the 2n times -1, all divided by n factorial 2 to the n, 2n plus 1. And then over here, 1 raised to anything is just 1, so I can just ignore that. So -1 to the n over n factorial 2 to the n, 2n plus 1. Now what do we have here? We have this -1, and we have this negative, so that's a plus, but also -1 to the 2n is always greater than 0. So all this just ends up changing to having those two terms added together. So it's just -1 to the n over n factorial, 2 to the n, 2n plus 1 on bottom. And then, like we said, we can just ignore that. We took care of those so that it's plus. So this is just plus -1 to the n, or how about 2 -1 to the n's. So now we've collapsed it down into a single, just a single term there. So now as I rewrite over here, now I'm ready to actually do some computation. So I'm going to pull this 2 outside. So I'm going to say 2 over the square root of 2 pi on the outside times n equals 0 to infinity, 2 to the negative, oh, I already wrote my 2, excuse me, -1 to the n over n factorial 2 to the n, 2n plus 1. And so we want to say what that's approximately equal to, right? So we're trying to get an approximation for this integral, and we want to go to 3 decimal places, right? So accurate within 3 decimal places. So we want to just go ahead and start adding up our terms. So I'm going to have 2 over the square root of 2 pi. And the first one here is going to be a 1 on top divided by 0 factorial 2 to the 0 times 1. And then I'm going to have plus 2 over the square root of 2 pi. And then I will have a -1 on top, 1 factorial 2 to the 1 times 3. Plus 2 over the square root of 2 pi over, now it's back to +1, 2 factorial 2 to the 2nd times, and if you put a 2 in there, you get 5. Plus 2 over the square root of 2 pi, -1 over 3 factorial 2 to the 3rd times 7. All right, and as we're going here, we want to be checking how big each of these things are. So because remember, this is an alternating series, right? It goes plus, minus, plus, minus. So I want to go and alternate back and forth, so I need to keep track of when I have the desired amount of accuracy. So this first one here is 0.7979. This second one here is 0.1330. This one is 0.0199, so we're getting there. This one is 0.0024. So not quite, right? So we're not quite out to 3 decimal places. So let's go another term, plus 2 over the square root of 2 pi, 1 over 4 factorial, 2 to the 4th, times 9. All right, and I compute that one, and that one's going to give me 0.00023. So now we're out past 3 decimal points. The next one that I'm not actually going to add, we'll just note that this next one would have been 2 over square root of 2 pi, 1 over 5 factorial, 2 to the 5th, times 11. That one would have been about 0.000, one more 0, 19. So that one's definitely not necessary to keep. So I keep these 5 terms, and these 5 terms give me approximately 0.683. And remember how we started the problem, we said that based on our knowledge of statistics, the answer should be about 0.68. But understand that this integral that we did is not one that you'd be able to do with your traditional integration techniques.